Okay, so in this video we're going to talk about the analysis that you can do inside a tool like MATLAB and Simulink, and but we're going to start off back in working model 2D to really motivate the type of analysis that we need to do. All right, so 2D is really good because it does contact so well, and in kind of like real time you can see the mechanisms in action that lead to the tip over. Right, and for this video though, I added one measurement. So this is what I call the rear axle. Essentially, that the tire is connected into the vehicle via the rear axle, right? And so we're measuring the force carried by that right here. So let's hit the run button. And you'll see it starts off positive as it carries the weight of the vehicle and so forth. But as the movement occurs and it begins to tip, well, it turns out that obviously it'll go to zero when it's no longer in contact with the ground. And so that onset of tipping is really when that point goes to zero. Right? And so we'll do some work on the Simulink side. We'll measure that force and we'll make sure we recognize when it's transitioning from a positive value to zero. In reality, it will go to zero. But because we're modeling it as I'll call it a connected constraint, which is connecting that vehicle to our motion platform, we'll see it'll go negative. But in a way we don't care because we know the condition that would lead to tip, and that's what we're observing in that figure right there. Okay, so let's get back to MATLAB and Simulink, and in this demo we'll definitely get a little bit more I'll say description of what's going on to model mechanics using the tool called Simscape Multibody. And we're seeing it a little bit at this top level as we see lines without arrows. And the basic idea of Simscape Multibody is it's a structural description that takes place in a two-dimensional schematic. And these are what they call transform blocks. And this is essentially how we assign location of these coordinate frames, these coordinate systems. And that number might, from the earlier videos might be familiar to you, but that's essentially a positional offset. And that one, what is it? It's basically where our drive connection is for the motion platform. Anyways, let's just kind of jump into it. And it means that we need to go in here and we need to make some measurements. So most of these are bodies, and we'll perhaps go and look at a few of them. But it's really these ideas of bodies and joints. And if you're new to Simscape Multibody, and it really actually took me a little bit of time to actually recognize this, the lines themselves actually represent frames. And that's why we see a lot of these blocks marked with terms like CS, coordinate system 2, coordinate system 3, and so forth. All right. But anyways, in previous videos we talked about how we're modeling that rear axle connection via two joints. One's a spherical, the other is a spherical joint in a slot, and we want to measure that force. And so I come in here and I go to composite forces and I type in constraint force. Right. Now there's a little bit of work to be done, and in a way maybe I don't have space for it, but there's also this general notion of really kind of divide and conquer and go down with the depth of detail that needs to be there to get the information that we want. All right, and so we'll turn this into a subsystem, right? And it's kind of all the same stuff. We essentially got these connectors. Now we want to have that go to an output, and in a way, the next, I'd say, 2 minutes is to kind of show how we do that. All right, so I want to maybe give myself a little bit of space. I also want to kind of accommodate, I'd say, some important conventions that are already being introduced. And so I'm going to match the names on the block itself. And so my external ports will be called B and F for base and follower. All right. Okay. Now this looks like an arrow that we're familiar with, but notice it's hollow, or you might say it's got a white interior, and that's an iconic image that's indicating that that's a physical signal. All right. And Simulink really just wants numbers, and it kind of relies on us to understand, if this is physical or what it really represents. But because we're working with a physical simulation tool like Simscape Multibody, we need to tell it as it goes to Simulink. Oops, there. what's the output unit? What does that represent? And so we're measuring a constraint force, and I'm going to type in newtons. All right. And that this is also a force for a three-dimensional mechanical tool, and therefore what it really is a vector, right? And so I want to be attentive to that. All right, let me double click, type in DMUX, that stands for DMUX. It means I can kind of break that signal out into its three components. All right, and so by default DMUXs come with 2, but I can make it 3 very quickly. And the one I really care about is that vertical one. That's basically what we're just measuring in Working Model 2D. And so that's what I'm going to output. And I type in OUT. And I will label that F sub Z. Okay. Now I'm going to basically attend to the other 2 measurements. And we're not going to use them soon. So for right now, I'm going to just kind of do what I think is the best practice, and we'll just kind of terminate those signals right here inside the subsystem. Right? And we're almost there. This last piece is really kind of addressing, again, convention. And that for every constraint, every connection, there's equal but basically opposite forces acting. If I'm pushing this phone against my hand, well, there's a force on my hand that way, but there's a equal in magnitude force, but opposite in direction forces acting on the phone, right? And so the convention that people work with is they say that for any kind of connection, if it's in compression, that's negative, and if it's in tension, that'll be positive, right? And since this is the rear axle force, we want that to be in compression, with the, ultimately through the ground contact with the tires. So anyways, let's go in, and that's an easy fix, and we'll just get a gain block in here. Okay. And with that, I kind of have what I want, right? And we're going to do this a couple of times, and so I'm going to kind of go do this and edit it out, but we'll do it for the rear axle, space bar, and then we'll do it for the front axle. And with regard to forces that are kind of acting on the whole system to essentially flip it over, or could be, we'll see that the connection with the rack for the forks will be an additional one, and then essentially the inertial load for the full vehicle. Right, so I'll make an acceleration measurement from here. So I'll be back in the video will be back in 2 seconds. Okay, so I got those forces set up for these 3 components, and I'm going to do something that's visually helpful. I'm going to select these 2, and then third, I'll select this one, and I'll go to Format, and I'll say match the size of the third one, and then I will also make all these guys blue. Okay, now I'm going to do a little bit more effort on, let's see, where's it? There it is, the rack weld. Okay, and so for the rack weld, this is essentially, we can perhaps see it best here, that we created, 2 pieces of this rack that goes up and down, but one of them is really fixed directly to the vehicle, and there is a weld joint associated with it right there, and it carries both the force of the rack as well as the green box that the forks are carrying, as well as the weight of the forces, and as well as the moment that's created by that is going to be the torque. All right, and so we're making a measurement of both right there. All right, so the last piece will be, let's get the acceleration of the full vehicle, and through that then we're going to be able to set up the force and moment balances that will allow us to kind of analyze the conditions for tipping. Okay, and so acceleration is really about connecting into the frame. The essentially is defined, or basically the frame that's defining the center of mass location on that solid. So it's connecting right there. That's called R, right? And this is a selected from here, transform sensor, which allows you to measure all kinds of cool stuff, but I'm measuring acceleration. So X, Y, and Z are checked, and from that we build our measurement. Pretty good. All right, so what are we going to do with this? I'm going to go to here. I just kind of did some work on this over the last week or so, which is a calculation. We'll kind of tour it a little bit of, here, I'll make this bigger on format. Let's put the lettering, we'll make it like 20, right? So moment, and it really should be called force and moment calculation. And you'll see both are measured right there. We're going to kind of show that we are calculating correctly, and with this we'll kind of understand the components that are going to essentially drive the tipping of the forklift. All right, so first one, it's right here. Trying to line it up, yes, so I get a straight line right there. So the front axle connects in right there. For the rack weld, torque is the second one. Let's drag it out. Okay, let's try it. Okay, that seems to be coming out now. All right. So torque, force, the vehicle acceleration is right there. And these are all the things we just created. And that the front axle, of course, will be the combination of the right side and the left side. Right, and so we're using add block. Okay, and so I'll just put in both components from the right and the left side. And with that, I think we got it. And let's go ahead and hit the run button. Let's kind of look at the scope. This could be a measurement. On the top will be force, on the bottom actually the top is torque and the bottom is force. And since the signals are labeled, we'll see that on the scope in a second. Okay, so simulation runs just like it did before. Right. Now here I want to make sure you see the scale. This is 10 to the minus 4. The tires we haven't really accounted for, but I did make them very, I'd say, small in mass, and therefore we are looking at a pretty small number. Right. You can kind of do this sort of stuff. So it might not be obvious yet, but that's a validation for me. And maybe the best way to see the validation is let's look at all these measurements. Is there a need to? Well, I'll show just very quickly. All right. That what I did in this block was I did a torque calculation and I did a force calculation. It's probably easier to understand the force first, and so we'll see, everything mass and gravity is right here, so mg obviously is a component of force. This is for the red vehicle only, all right, and everything else is really, loads that are going to be applied to it. And so there'll be the front axle force right there, right, the rear axle force right there, and then the force associated with the rack. All right, and so the moments are a little harder to explain. Again, I'll kind of point to work in Model 2D that it's a moment calculation about the front axle, and there'll be various moment arms. I think you can kind of see them here. The distance between the two axles will be a moment arm used to construct the moment associated with the rear axle, and there will be one associated with the force there, as well as one associated with I'll call it the center of mass of the vehicle, for its gravitational moment. And there are two others, and I won't elaborate too much more on that, but I'll just say that it works, and it's kind of good to look at this from the data inspector. You'll see that the logging of these signals was set up in that block I had created too. And so you'll see kind of vehicle force, just like we saw it in the scope, but when we compare it to the front axle force and the rear axle force and let's see, the F, the force associated with the rack connection. Those are the forces that essentially all add up to 0. Oh, there's one more, of course, mg. Mg is a really important one. It's the biggest one. All right, so these all add up to 0. And that condition of tipping, you can absolutely see it right there. That's when the rear axle in purple transitions from positive to negative. In reality, it will never be able to apply a negative force and tug down the vehicle. It will go to 0 and it'll flip because there will no longer be a balance. All right, and let's see. I'll always show them clear subplots. Torque. These are all the components of torque. Rack moment, the acceleration torque, and then the gravitational torque. And likewise, all these add up to 0. And so, and that's what it's right there, the blue line. And I think I'll save for the next video really kind of the dynamics that kind of leads to this. But obviously, the key things will be the acceleration of the vehicle, and then the forces and torques associated with the rack connection and its movement with the big box. So anyways, we'll move on to that in the next video. All right, thank you for watching.